When we look at this valence bond theory with methane, we begin to have more of a problem. So looking at carbon and hydrogen. So here is carbon's valence electrons. We've got 2 in the 2s orbital, and we have 2 half-filled 2p orbitals. Hydrogen, as always, has a half-filled 1s. So just the simple overlap would predict that one hydrogen would overlap with this orbital, and that another one would overlap with that one, right? And so we'd get something like this, where we have this orbital, this p orbital overlapping with that hydrogen, this p orbital overlapping with that hydrogen. We've got this full s orbital here, and then there's just an empty p orbital. Predicts a 90-degree bond angle. But actually, CH2 does not exist. What we see is CH4 with 109.5-degree bond angles because it's a tetrahedron. So what this tells us is that an additional concept is needed. We're not going to just chuck the whole idea. We're going to say, well, obviously there's something we haven't thought about. So up to this point, we're assuming that the orbitals in the molecule are the same as the orbitals in the atoms that made up the molecule. But that's not necessarily true. When those atoms come together and interact to become a molecule, their orbitals can be affected by that. They can hybridize. So hybridization is a mathematical procedure in which we take the standard atomic orbitals and we combine them to form hybrid orbitals. Okay? And we're staying away from all the math of that, but there are people who do all the math. So when we hybridize these orbitals, they're going to correspond more closely to the actual distribution of electrons within the molecules. They're still localized on the individual atoms, but they're going to have different shapes and energies than the atomic orbitals did. So let's look at how this would work. The hybrid orbitals are going to minimize the energy of the whole molecule by maximizing the overlap. The more overlap there is, the more stable it's going to be. So the hybrid orbitals give us greater overlap because like the p orbitals and the d orbitals had lobes, right? And one lobe is on one side of the atom and the other lobe is on the other side. And if you're overlapping those p orbitals, you can only overlap with one lobe. You can't do anything with the other lobe. When it hybridizes, it gets more directed toward one side of the atom, and so we can get better overlap. Hybridization does not happen without cost, though. There's energy required to do the hybridization, and so it only happens if the payback is big enough. The payback meaning the stabilization of the molecule. What we're going to do is we're just going to look at the hybridization of the interior atoms, and we're going to assume that the terminal atoms, those that are only attached to one other atom, are not going to hybridize. So some general statements before we get into the details of this. When you hybridize orbitals, you end up with the same number of orbitals that you started with. So the number of standard orbitals added together always equals the number of hybrid orbitals. If you start with 3 standard orbitals and you hybridize them, stick them in the blender, you still have 3 orbitals when you're done. The particular combinations are going to determine the shapes and energies. And the particular hybridization that comes out is going to be the one that stabilizes it the best, that has the lowest energy. The calculations for all of this are way beyond what we want to do in Chem 1A. So what we're going to do is we're going to use Vesper theory to help us predict what the hybridizations are. Okay. So The first one is that we'll look at is sp3 hybridization. And so here are standard atomic orbitals for carbon. There's the s orbital, and there's 3 p orbitals. And the p orbitals are higher in energy than the s. When we hybridize and take all 4 of these orbitals and hybridize them, we come out with 4 orbitals that have the same energy. They're degenerate. And so that energy, of course, is going to be between these two. So it'll be higher in energy than the s, but a little lower than the p. Kind of like averaging, right? This is called sp3 hybridization because it involves 1 s and 3 p orbitals. So the carbon atom by itself had 2 half-filled orbitals, 1 full orbital, and 1 empty orbital. So when we looked at overlapping orbitals, we predicted that we would just overlap these 2 with hydrogens. Now combining these and making them equivalent in energy, each of these electrons is going to occupy its own orbital. There aren't going to be any paired because they don't have to pair. And so then we get 4 half-filled orbitals. Each of those can overlap with a hydrogen, right? What does that look like when you hybridize them? This takes a little bit of imagination. So you take this shape, and that shape, and that shape, and that shape, and you combine them together mathematically, and you end up with these guys. And you thought the s and the p orbitals were kind of weird. This is an sp3 hybrid orbital. So what I'd like you to note is that it does still have 2 lobes, but now one of them is much larger than the other, right? Here on the p orbital, they were equal in size. But because of combining all of these together, we're going to end up with these 4 new things. And so these had angles, we had 3 different angles, if you will, orientations. Now we've got 4. They're separated as 4 things would get away from each other. And what's that shape? Tetrahedral. So each of these orbitals has the same shape. It has the same energy as the others, but they're oriented in space to form a tetrahedron. So we often draw it like this. When we draw it like this, we are not showing the little tiny lobe because it makes the drawing really hard to look at. But each of these does have a little lobe on the other side. Okay? Any questions? Is this disturbing? Little, yeah. What are they doing? So when we hybridize carbon's valence orbitals, we end up with 4 equivalent sp3 orbitals instead of an s and 3 p's that were different. So now the electrons are going to do just like they did in the p orbitals, where they take their own bed first before they pair up, right? So here they can all have their own orbital. So they're going to have parallel spins. That's what Hund's rule tells us. And now we can take these the purple, sp3 orbitals, there's 4 of them, and they can each overlap with 1 hydrogen. And that gives us a tetrahedral geometry, and it gives us a formula of CH4, which is what we observe. Carbon and hydrogen form methane, and the formula is CH4. The carbon has single bonds with 4 different hydrogens. Hybrid orbitals can also accommodate a lone pair, although the presence of the lone pair makes that atom less likely to hybridize, but it can. So ammonia has sp3 hybrid orbitals. Let's look at nitrogen's orbitals. It would have 2s2 2p3. Yeah. So if we drew orbital diagram, 2s and 2p, 1, 2, 3, 4, 5. So because there's this lone pair, the nitrogen is a little less likely to hybridize, but it still can. When it hybridizes to form sp3, now we've got 5 electrons in there, so one of them is going to be a lone pair. So here in the purple again, we have the sp3 hybrid orbitals. 3 of them are half filled, and those are going to overlap with hydrogens. And this one has a lone pair. Again, this predicts tetrahedral geometry, 109.5 degree angle, but the bond angle is 107 because the hybridization is less complete. It hybridizes, but it doesn't hybridize completely, and so that is what is affecting the angle. That makes this angle a little closer to the unhybridized angle of 90 degrees. Yes?
Does that hybridization only happen when it's in a compound?
It only happens in a molecule.
Or molecule?
Yeah. So in order to hybridize these orbitals, that causes an increase in energy. When bonds form, a lot of energy is released. And so it's a little bit like, a business deal, right? So you have to invest some money to get your property ready, but then there's a payoff when you're able to lease the property to someone, right? So you're not going to get your property all fancy if you're not going to be able to lease it for enough, right? You're not going to spend $2 million updating your garden shed if you can only rent it for $5 a month, right? Or something silly like that. So the hybridization only happens when there's a payoff, when a bond forms that releases energy. Any questions?
The repulsion of that lone pair will lessen the hybridization of the other hydrogen bonds.
It's not really the repulsion, it's just the existence of the lone pair. The fact that there's a lone pair is going to reduce the degree of hybridization, and so it's not complete. And so then these angles, instead of being perfect, 109.5, they're a little closer to the 90 degrees that would happen if you just had overlap with the p orbitals. You'd have 90 degree.
If you go back to the hydrogen example of the overlapping orbitals, does that mean that they're getting further away from each other? Or
That wouldn't affect, that would be the bond length, the distance between the two atoms. Here we're talking about bond angle, the difference, the angle between the angle of hydrogen, nitrogen, hydrogen, whereas the bond length is talking about the distance between the hydrogen atom and the nitrogen atom. And that's not significantly affected by the presence of the lone pair. So valence bond theory and VSEPR theory both have an explanation for why we have this decreased angle with the hydrogens, but the explanations are different. VSEPR theory says, well, the lone pair is more repulsive or it takes up more space. This says that the hybridization is less complete. Any other questions? You can also have hybridization with an s orbital and 2 p orbitals. So here we have our original standard atomic orbitals, and if we take the s and 2 of the p's and hybridize them, we're going to get 3 sp2 hybrid orbitals. Because we started here in the box with 3 orbitals, so we have to end up with 3 orbitals. And that p orbital that wasn't included in the hybridization is just still there where it was. So it's called sp2. So this is combining an s orbital and 2 p orbitals. You get 3 equivalent orbitals. And again, they resemble the p orbitals, but they're lopsided, right? This end's a little bigger and that end's much smaller. Well, three things, they're going to orient themselves symmetrically in space. How do three things arrange themselves? In Vesper theory, 3 electron groups would make what? Trigonal planar. So these are going to make a trigonal planar shape. That's how they're oriented in space. Let's look at H2CO. This has sp2 hybrid orbitals. So the carbon is the central atom. So here we have the carbon. Here are its valence electrons as an atom. It's going to hybridize, and we're going to end up with sp2. 3 of those, they each have 1 electron, and then a leftover p orbital here, and that's going to be half filled as well. Here you've got your oxygen. The atomic oxygen has 2 p orbitals that are half full. The hydrogen has a half full orbital. So valence bond theory is talking about the overlap of half filled orbitals. So this hydrogen can overlap with one of those sp2 orbitals, and the oxygen could overlap one of its p orbitals, and then this is H2C, and we'll get another hydrogen doing this one, and then we've got this leftover p orbital, and we've got our oxygen with a leftover p orbital. How's that? It's beautiful. Yeah, and you're going to have to try to draw these things. It's fun. So here in the purple are the hybrid orbitals. Okay, so carbon made an sp2 hybridized set of orbitals. And those make a trigonal planar geometry. So this green here is representing a horizontal plane. So we've got these 3 half-filled orbitals. And one overlaps with hydrogen, and this one overlaps with hydrogen, and the third one overlaps with one of the orbitals on oxygen. Remember, this oxygen had 2 half-filled orbitals. So one of these is going to overlap with one of those. But then we also had a p orbital on the carbon and a p orbital on the oxygen that were not hybridized. They were both half full. So this is the p orbital. This one's going up and down, and that one's going up and down. Those can overlap side to side and form a bond. And that's what makes a double bond between the carbon and the oxygen. The first bond is an end-to-end overlap of a p orbital on oxygen with an sp2 hybridized orbital on the carbon. And then the unhybridized p orbital on the carbon and the unhybridized p orbital on the oxygen overlap side to side. So when you have end-to-end overlap, that's called a sigma bond. And I think of sigma as being symmetrical, and the sigma letter itself is a circle with a little tail on it. If you look from carbon to oxygen along this bond, it would look like a circle, right? A cylinder. It's symmetrical. So that's what the sigma bonds are like. This side-to-side overlap is called a pi bond. Not exactly sure why, but the sigma is the symmetrical one. The pi bond is the other one. Any questions?
What about the unhybridized orbital? How do you determine that it's going to do that?
As opposed to carbon making sp3?
Yeah, as opposed to some of them completely hybridized.
Well, what we're going to do, mathematically, they can do that. We're avoiding that. So what we're going to do is, and I'll show you this in a minute, we're going to use what we've learned about Vesper theory to predict this. And it actually works pretty well.
So how can you predict hybridization on high level energy combinations?
Well, hybridization,
You can use the component of using the pi and I don't know how to use it. I watch video, but you have to drop one side when it's all.
yeah, let's continue on, and I've got a lot more explaining to do. And then hopefully some of it will clear up, and that if not, we'll deal with it then. So the pi bond happens when p orbitals overlap side to side. So here you've got your half-filled p orbital. In that example, one was from carbon and one was from oxygen. And they're going to overlap side to side. Right? They're like coming up next to each other. So these kind of smear out together and overlap. This is the sigma bond where they overlap end to end. Which one looks like it would be a better overlap? The sigma. The sigma is better because, I mean, you can get a lot of this overlapping with a lot of that. This is kind of strained because you can't get these nuclei too close together. And so they're like, the pi orbitals are kind of stretching over to reach the other one. Whereas here they're going to head, and they can just overlap really nicely. So sigma bonds are end-to-end overlap, and pi bonds are side to side. We label these with a notation, and you're going to need to use this notation on the worksheet today. So this is that same molecule that we've been looking at. So this is a pi bond. So this is pi and then a semicolon. And the overlap is between a p orbital on the carbon and a p orbital on the oxygen. So that's what that notation means. This bond right here is sigma. It's between a carbon and an oxygen. But now the orbital that's overlapping on the carbon is an sp2 hybridized orbital. And on the oxygen, we have the unhybridized p orbital. These two bonds are equivalent. They are sigma bonds, and they are the overlap of an sp2 from the carbon with the s orbital from the hydrogen. Any questions?
What is the difference between the sp2 and the s?
Well, the s orbital is spherical, and the sp2 orbital, it has one large lobe and one small lobe. So we get a lot more insight into the molecule from valence bond theory, because this shows us that that double bond between the carbon and the oxygen is actually two different types of bonds. Whereas the double bond in the Lewis theory, it looks like it's just, two identical bonds, right? But in valence bond theory, the double bond that we see in Lewis theory is always one sigma and one pi bond. Those pi bonds are usually weaker because the side-to-side overlap is less efficient than the end-to-end overlap. And what we observe in experiments is that the pi bond is easier to break. You can break the pi bond without breaking the sigma bond. It happens a lot in organic reactions. And valence bond theory helps us to understand why that could be. More colorful pictures. This also explains why double bonds cannot rotate. Okay? This model I made yesterday. Here I've got a carbon-oxygen double bond. And these model kits are cool because it kind of works out this way. You can't rotate that oxygen that's double bonded to the carbon because the double bond won't let you. But here, this hydrogen, I can twist this guy around, or that oxygen, any of the single bonds, you can rotate. And when you look at valence bond theory, it makes sense. So here we have ethane. There's a single bond between these two carbons. And because it's an end-to-end, you can rotate. And so this can rotate around. When we have, I'm sorry, that's not ethane, it's dichloroethane. So we've got two chlorines on here. When you put a double bond in there, dichloroethene, the double bond is one sigma bond and a pi bond. This is one pi bond, right? Because it's two lobes of the same orbital here and two lobes of that orbital. When they overlap side to side, it kind of looks like it's two bonds, but it's only one. So this red is all one bond. In order to rotate these two atoms, you'd have to break this. Yes?
What does a double bond with a pi bond look like? Like, how would it look differently compared to that one?
Well, this is a double bond with a pi bond.
Oh, it is.
Yeah. So you've got a double bond is always a sigma bond and one pi bond. You don't see a double bond that's two pi bonds. Yes?
How come they don't show the other orbitals on chlorine?
On chlorine?
Yeah, they shouldn't have like the.
Yeah, there are other orbitals and lone pairs and stuff on the chlorine atom. What we're focusing is the interior atoms. We're assuming that the terminal atoms do not hybridize, and that just makes everything easier. In truth, they do hybridize somewhat, but we can ignore it for what we need to learn. Okay. Any other questions? These are space-filling models. Here is the I'm blanking. Yeah, there's actually a fourth hydrogen hiding behind there. So this is, we're looking at these same two molecules. So this is the dichloroethane with the single bond, and you can rotate it. And so you can twist it around, and the chlorines could be opposite from each other, or they could be near each other. It can rotate. When we have the double bond in there, because of the overlap, and there's no rotation. And so that brings up the possibility of having two different molecules that have the same chemical formula. And they differ in how they're arranged in space. These are called isomers. So here we've got the chlorines on the same side of the double bond. That would look like this. And here we have the chlorines on the other side of the double bond. And so they have to have different names. This is trans and this is cis. And those are things you'll learn about in organic chemistry. But you can't make this one into that one without breaking a bond. You have to break the double bond in order to rotate it like that. When there's a single bond, there's free rotation, and these guys just twist around. Any questions?
The answer, triple bond?
We'll get to triple bonds.
So would that be considered resonance?
No, this is not resonance. Because there's no rotation around that double bond, these are actually two different molecules. And they have slightly different chemical and physical properties. This is just rotation.
So they would have different properties?
They would have slightly different properties, yeah.
So it would be easy to separate them?
It wouldn't necessarily be easy, but it would be possible. Yeah, you can't separate this from that because this doesn't stay this. It's always wiggling and moving, right? But these guys are basically frozen.
Do they form like let's say you had those things and you're trying to form, do they form like different ones? Let's say you're just trying to get this one with that one form as well.
Yeah, it depends on the reaction. There are reactions where you can get just the cis forming or just the trans forming, and that is part of the puzzle in organic chemistry, is when you look at the ratios and of which isomers are forming, it's really pretty interesting. Okay, so we've talked about sp3 and sp2. What if you just have an s and a p? So here are atomic orbitals, and now we're going to hybridize the s with one p. We'll get two sp hybrid orbitals. And then we have two unhybridized p orbitals. So when we hybridize these guys, again, we've got a very similar shape to the sp3 and the sp2, but these are resembling Well, they're just basically the same shape. The biggest difference between sp, sp2, and sp3 is their orientation. Because here we've got two of them, and so they're going to be opposite to each other. Again, we are not showing this little lobe when we draw this picture. So we've got these two hybrid orbitals here, and then the unhybridized p orbitals are going to be perpendicular to this one. This one was the p orbital that was along the x-axis, and so then we'd have an unhybridized p orbital that's on the y-axis and another on the z coming in and out of the plane. So let's look at acetylene. Well, it says draw the Lewis structure, but really, in essence, that is the Lewis structure, but I guess I must have put that there for some reason. So the only way we can draw a Lewis structure for that is to put a triple bond between the two carbon atoms. Acetylene has sp hybrid orbitals. So here's our carbon atom, and we're going to hybridize the s with one p orbital, and so we're going to get these two sp orbitals, and then we're going to have two unhybridized orbitals. And these are close enough in energy that they're just going to all the electrons are going to take their own orbital. So we've got the possibility for 4 bonds. This also shows us why that little trick I showed you with the number of unpaired electrons in the Lewis structure. Carbon wants to form 4 bonds. This is why carbon wants to form 4 bonds. So how does this triple bond work? Well, here's the carbon, and here's one sp hybrid orbital and the other sp hybrid orbital. So this carbon's sp hybrid orbital overlaps with the other carbon's sp hybrid orbital. And that gives us a sigma bond between the sp hybrids on both atoms. We also have 2 unhybridized p orbitals on this carbon and 2 unhybridized p orbitals on that carbon, and they can overlap. So this one overlaps here and here. That forms a pi bond, and then this one that's sticking in and out overlaps and forms a second pi bond, and that's the triple bond.
They're perpendicular.
The red, this and that red, and the purples are perpendicular. They're oriented the same as the 3 unhybridized p orbitals would be.
So it's one sigma and 2 pi's?
One sigma bond and 2 pi bonds gives you the triple bond. And so this is predicting a linear geometry. And that's what experiment tells us. Vesper theory tells us this is going to be linear as well, because you look at this carbon and it has 2 groups. 2 groups make a linear shape. There's no lone pairs. And this one has 2 groups in a linear shape. So Vesper theory predicts that this molecule is linear, and valence bond theory predicts that as well. Any questions? Mm-hmm.
Just to clarify, the 2s electrons are always going to be used up in a hybrid-like bond.
Right.
In any type of bonding.
Yeah, so you don't have a hybrid between p orbitals only, because they're already degenerate. It always involves the s orbital and 1 or more of the p orbitals. And then the electrons are going to spread out differently than they did in the atom. Okay, so that's what happens with the s and the p's. But remember we talked about elements in the 3rd row, the 3rd period, can expand their octets, right? And it was a little mysterious about how that would happen. In valence bond theory, this corresponds to including d-orbitals in the hybridization. Because how could you get more than 8 electrons around an atom if there's only 4, right? An sp3 hybridization gives you 4 orbitals. That can hold a maximum of 8 electrons. So how do you get more? You have to pull in some other other orbitals. So the energies of the 3d orbitals are similar to those of the 3s and the 3p. They're not the same, but they're similar. They're close enough that they can combine. So here we have S, P, and D. You can take the S and the 3 Ps and one of the Ds and combine those together. You're starting with 5 orbitals. You have to end up with 5 orbitals, right? And now this is called sp3d. It's got 1 s orbital in it and 3 p orbitals and 1 d orbital all smushed together. What's left? 4 unhybridized d orbitals. They're just sitting there the same. So these 5 hybrid orbitals are going to be degenerate. They're equivalent, right? And so they're going to arrange themselves in space like 5 balloons would, that trigonal bipyramid shape. Okay, so each of these is the large lobe of one sp3d hybrid orbital. Okay with that? Because we really didn't want to see how that was combined from the original pictures. But here's an example. So arsenic pentafluoride. So the arsenic can have sp3d hybridized orbitals. And so we have 1, 2, 3, 4, 5. And they can each form a sigma bond with a fluorine atom. So each of these bonds is a sigma bond end-to-end with an sp3d hybrid orbital from the arsenic with an unhybridized orbital from the fluorine. You okay with that? We can also pull in 2 d orbitals. If you pull in 2 d orbitals, now you're getting 6. They're called sp3d2. 6 equivalent orbitals make this octahedral shape. They're going to spread out equally in 3-dimensional space. And then each of these can overlap, can make a sigma bond with something else. So here's sulfur hexafluoride. Sulfur is hybridizing to the sp3d2. So it has 6 of those, and each of those can form a sigma bond with the p orbital of a fluorine atom. Again, we're assuming that these terminal atoms are not hybridizing, just to keep things simple. Well, you're probably saying, how is this simple? It's simple compared to what we could be doing. Okay, so, and this is a question that came up earlier. How do we know what hybridization scheme is going to work? How do we know? Well, the rigorous method is you calculate the degree of hybridization and which orbitals are hybridized. You try all these different combinations. You see which one's going to give the lowest energy, and that's the one it's going to have. That's the rigorous method. That involves computers, right, and lots of math. We're not going to do that. We're going to go with good enough for Chem 1A. So, right? It's good to strive for excellence and everything, but you can't do everything. And so there are some places in life where you have to say good enough is good enough. And here we're saying good enough is good enough. We're going to pick the hybridization scheme by looking at the electron geometry on the interior atom. So we're basically going to use VSEPR theory to predict what it does. Not 100% accurate, but like 95% maybe? I don't know exactly, but 95 is pretty good. Right? That'll get you an A in a class, right? Yeah. So you got to give up our perfectionism and just settle for good. So this is how we predict. You look at the number of electron groups. So if you have 2 electron groups on the central atom, then your hybridization scheme is going to be sp. So you look at the central atom and you count the groups. 1, 2. See what I wrote on my fingers? SP. So 2 groups sp hybridized orbitals. What if you have 3 groups? S, P, P, sp2. If you have 4 groups, sp3. Okay? Then I get to the point where I'm going to run out of fingers. 5 groups, sp3d. You need 5 orbitals, right? Here you need 6, sp3d2. So we're going to draw the Lewis structure. We're going to look at valence bond theory and predict the shape. We're looking at the number of groups on the central atom again, but now we can use that to predict the valence bond theory's hybrid orbitals. So, set of instructions. Start with the Lewis structure. Use Vesper theory to predict the electron geometry on the interior atom or atoms. Pick the correct hybridization based on the electron geometry, based on the number of groups. You don't really need table 10.3. Just use your fingers, right? There's 3 groups. 1, 2, 3. Oh, sp2. And if you want to write on your fingers during an exam, that's fine. You can go ahead and do that. So you pick the hybridization, then you sketch the model. You sketch the molecule. Start with the interior atom and its orbitals, and then overlap them with the terminal atoms, and then label the bonds. So we're labeling them as sigma or pi, end to end or side to side, followed by the type of the orbitals that are overlapping. I think we've got an example coming up. Let's do this one. So xenon tetrafluoride. The first thing we have to do is the Lewis structure, right? So we've got xenon, and we must have the 4 fluorines around it. And then we have to ask ourselves, well, how many electrons? So we've got 8 from the xenon. There's 4 fluorines, and they each have 7. So that's what, 36? Is that right? So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Where do I put the rest of them? Central atom. So there's 34 and 36. There's our Lewis structure. How many groups around the central atom? 6. So we have 6 electron groups. That means we need to take 6 orbitals and hybridize them. So S, P, 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 and where do we go after that? D, and we need one more. Yep, 2 Ds. So we've got the S, we've got 3 Ps, and we need 2 of the Ds. That gives us 6 orbitals, okay? So then drawing this is the fun part.
What was that, Jake?
6 things? It's an octahedron. Okay, so here's our sulfur in the middle. No, we don't have any sulfur in this. Here's our xenon. And so now I'm going to try to draw 6. And what I'm going, you have to draw these things on the worksheet. What I'm going for is I need to be able to tell that you tried to get it right and that you tried to do 3 dimensions. So we're going to have one up and one down, and then we're going to have one kind of going to the back and one kind of going to the front and one kind of going to the back and one kind of going to the front. Now that's pretty ugly, but it's okay. And then the fluorines, what are the fluorines going to overlap? So what are the valence electrons in fluorine? We've got 2s2, 2p5, right? So if we looked at the orbital diagram for fluorine, we'd see that it has one p orbital that's half full. That's the one that's going to overlap with the xenon. And that's why fluorine usually forms one bond. So I've got fluorine down here, and there's its p orbital. You know what? I'm going to use color since I can, because... So here's fluorine overlapping, and here's a fluorine overlapping, and there's a fluorine overlapping end to end. And here's another one. And here's another one. Oh, you're right, there's only 4.
So the things coming on xenon are just the electron groups? Those are just pairs?
I'm having a brain fart here. Okay, so getting carried away. So we've got our orbitals. There's 2 that are lone pairs, right? So we got to take care of those.
I think those are the ones going up and down.
Those are going to be up and down, right? Because those are, well, actually, we usually do the arrow thing in here. So there's a pair of electrons in that one and a pair of electrons in that one. We're going to put those opposite to each other, just like we did in Vesper theory.
What are those?
The lone pairs. These are the hybrid orbitals,
So
the
you
sp3d2.
draw all the bonds like that?
Well, no, these are the hybrid orbitals. There's 6 of them. And so there's 6 different lobes coming out in the shape of an octahedron. I know it's weird. 2 of them have lone pairs of electrons. That's where I got carried away. This is so exciting. Just got carried away. So then okay. And thank you for stopping me, because we're not even going to get to molecular orbital theory. Dang. That's okay. I think your heads might explode. This is enough to grasp for one day.
So, just out of curiosity, the p orbital can have a maximum of 3 orbitals. And you say we really wanted to have a really complex molecule. Is the D capable of having 10?
Well, there's,
Hybridization.
I suppose in theory that you could have sp3d5 hybridized orbitals, right? But I don't know of any that do that. In Chem 1A, it just goes this far. 6 groups is where we stop. Now, we're not done yet because we need to label the bonds. Okay. Ooh. So there's only one kind, though. Yes? What is the point in drawing it? That's a good question.
It's kind of redundant if you understand. When you do the Lewis dot structure, you kind of understand already what you're doing. But for like drawing it,
Well, drawing it is probably redundant for some people, especially when we get into the double and triple bonds, though. I think at least when you're starting out, you have to draw it. And so maybe think of drawing it as proving that you understand it. Because otherwise I can't get in your head. You know, some of you are getting it and some of you are not getting it, right? When I look at your drawings, I'll have a better idea of what's going on. So I guess maybe that's the point. The point is not to torture you. Just you know.
Gotta do some work.
Gotta do some work. Okay, so each of these bonds is going to have the same label. Okay? What kind of bonds are they? Sigma or pi? They're sigma. And so sigma and a colon, and then they're an overlap between xenon and what kind of orbital on the xenon? sp3d2. And fluorine, and what kind of an orbital on the fluorine? Just an unhybridized p orbital. It's a dash. This is a dash. So xenon sp3d2 dash fp. So it's the p orbital on the fluorine and an sp3d2 orbital on the xenon. And each of them is the same, so you don't have to you don't have to label it 4 times.
This is
Yes?
Why would the F for the fluorine have a P instead of an S?
That's a good question. Why would the fluorine have a p orbital to overlap instead of the s orbital? So what I drew down here are the atomic orbitals for fluorine. Again, we're assuming that the terminal atoms do not hybridize at all. So what's the orbital that's half full? It's a p. That's why.
So if it was lithium, it'd be LAS.
Which one?
If it was lithium, it'd be LAS.
Yeah, if it was lithium, lithium's got a half-filled s orbital. When hydrogen overlaps, all it has is a half-filled s orbital. Yeah.
And then on the xenon, why is it that it's P3, P2?
Why is it sp3d2? Because we look at the Lewis structure, and Vesper theory predicts that it's going to have an octahedral shape. We look here and we see that there are 6 electron groups on the central atom. So to get 6 things, we have to hybridize 6 atomic orbitals. Yes?
Okay, so beryllium, it forms a bond, but it has it in the 2s ones are full. Does that mean that they jump up to the 2p, or how does that work?
Well, that's a good question. Let's think about that.
Funky atom, man.
Beryllium is funky.
I don't like that guy.
In general, things that are exceptions to the rules are just kind of annoying, right? So let's just think about beryllium for a minute. So beryllium's got, 2s, right? So valence electrons, 2s. Well, what's a good guess for what it might do so that it could have some half-filled orbitals? Well, it could be an ion, but we're not doing it. What if we took these two and hybridized them? That would be sp, and then we'd have the p orbitals that are empty. And then beryllium can overlap and bond with 2 things. When we did the Lewis structure, I don't know. We're making stuff up, so it doesn't really matter. If we had beryllium and 2 hydrogens, that would be the Lewis structure, right? How many groups on the central atom? 2. So the hybridization is sp. So it works. Okay, good question. Oh, I was afraid of that. Okay. I think.
Will we be tested on beryllium, or is that just something we should know?
Just know that beryllium's weird. Boron's weird too. When I pick exam questions, I don't try to trick you on what I consider that. I consider that to be kind of a nitpicky detail. We have to talk about it because you're going to see it in the homework and stuff, and you just have to understand that, yeah, it does that. But I'm not going to try to trick you on an exam to see if you remember that. I'm more concerned with, can you do this other stuff that covers most of the things? So I'm just going to do one of these. Do you want to do hydrogen cyanide, or do you want to do carbon dioxide? I got 2 carbon dioxide, so we'll do carbon dioxide. Hydrogen cyanide was the first one. But we've picked this one. So I'll do the other one tomorrow for the Thursday people, and then you can watch that video if you really want to. Okay, so we need a Lewis structure. So there's our Lewis structure. Okay. How many electron groups in the central atom? 2. So what's the hybridization? sp, right? So the hybridization is sp. So sp is going to have 2 lobes, 1 on each side, and they're going to be opposite, right? So we're going to start with the central atom here, carbon, and here's its sp. So this is one sp, and that's the other sp. They're opposite to each other. Oh, you know what I should do? No, of course you don't know what I should do, because I haven't told you yet. I'm going to go with the book's color scheme. So purple is hybridized. So there's the carbon. What is the oxygen going to be doing? Let's look at the oxygen's valence shell. How many valence electrons? 6. 1, 2, 3, 4, 5, 6. So the oxygen is going to be overlapping a p orbital with the carbon. So here's the oxygen. Here's the other oxygen. Our Lewis structure is going to get in the way. Book uses red for p orbitals. So there's its p orbital, and there's the other p orbital. Okay? Well, this is showing double bonds, right? And when we look, so this was oxygen. Let's sneak the carbon in here. The carbon's going to have sp and unhybridized p orbitals, right? So it's going to be 1, 2, 3, 4. So this is our two sp orbitals, this purple one and that purple one. They're going to overlap with p orbitals of oxygen. Oxygen has another p orbital here that's half full, right? So that's going to form a pi bond. So here we've got, and the carbon has an unhybridized p orbital, right? And so these are going to overlap and form a pi bond.
Could you explain why it's pi bond?
Because it's side-to-side overlap.
Oh, but why would we make it like how we have?
Well, you can only have one sigma orbital. One sigma overlap. You can only have one sigma bond because this orbital is perpendicular to this one. It can't be on top of it, right? So we've got an unpaired electron in this one, and we've got an unpaired electron in this one. They're going to overlap side to side. Now, the carbon has one more unhybridized p orbital, and that one sticks out. So if this is the y-axis and this is the x-axis, this is the z-axis, the in and out, right? And this oxygen also has an unhybridized p orbital in the the z-axis, and those can overlap side to side.
I don't know what axis is.
Well, normally y is up and down, and x is side to side.
No, I don't even know what axis I mean.
Well, they could be on different axes, but these are easier to draw. If I made this the z-axis, it's really hard to draw, the whole thing sticking out at you. So that's why I picked it.
Why are you only looking at oxygen? Don't you need to look at the carbon, that structure as well?
Well, the carbon has, this is one of its p orbitals, and this is the other p orbital, these two right here.
Well, I guess what I'm not seeing that you drew carbon up there, so I'm not.
This is
following.
carbon right here.
No, you put 2s, 2p, that's your oxygen, right?
This is oxygen, and this, I'm sorry, this is carbon above it. I didn't label it. This is carbon.
And 5p?
No, that's an S. This is the sp hybrid orbitals.
I guess what I'm not seeing is you're just taking oxygen and then you're just putting the carbon into that hybrid, but don't you have to look at them both together to figure out where it's going? Not really.
We're assuming that the oxygens do not hybridize
Why are you assuming that?
because they are much less likely to hybridize, and because we can ignore it and still have everything be okay, because you don't want to do what happens when you don't ignore that.
I guess my question is why are you assuming that? How would you assume it in a different molecule? Which one's
Well,
not hybridized and which one's not?
In Chem 1A, you're always going to assume that the central atom hybridizes and that the terminal atoms do not. Never.
Only working on the central.
We're only looking at the central or the interior. Now, if you've got multiple interior atoms, you look at each of them separately. And the way we decide that this is going to be sp hybridized is we're looking at the number of electron groups. This has 2 electron groups. That's why I made it sp. So I've got my sp hybrid orbitals here. They each overlap in a sigma bond with one oxygen. And then I look at the other unhybridized orbitals. Carbon has 2 p orbitals. So this one and that one. And then oxygen overlapped one of its p end to end with carbon. The other one can overlap side to side.
It's gonna take some practice.
It's going to take some practice, and that's what we're doing in lab today.
I'm just gonna get it right now.
Okay, so let's label this bond. Sigma or pi? Sigma. And it's between what two elements? Between carbon and oxygen, right? What orbital on the carbon? An sp, hybridized orbital. And what orbital on the oxygen? P. Okay, that is the same as that one, right? Those are the same. How about this one? That's a pi bond. Whoops, got ahead of myself. Between carbon and oxygen. And what are the types of orbitals that are overlapping? Just p and p.
Why is one P and the other one?
The carbon does an sp hybridized orbital because there are 2 electron groups here. We're using Vesper theory to assist us in doing valence bond theory without doing lots of calculations on a big, powerful computer. So this 2 groups tells me sp. I need a hybrid orbital where I have 2 equivalent orbitals. And so the sp, one of them's on this side, one of them is on that side. That is something that's different between an sp orbital and a p orbital. In this oxygen, this lobe up here and this lobe down there are the same orbital. It's just one orbital. On this carbon, the lobe on this side is 1, and the lobe on the other side is a different orbital. Does that help? Does that help?
Can't be the same one.
Yeah, it can't be the same one.
So that was a SP2. You would, that drawing there, you would just like that little square over that way, and on the big picture, one of the sides would be purple now?
If this was sp2, then I'd take one of these boxes and smush it over here, and I'd have one unhybridized p orbital. And then one of these red p orbitals here would be gone, and I would have 3 lobes on the purple, and they'd make a trigonal planar shape. I can't just convert this because the angles would be wrong. Yes?
This is the oxygens. Now, one of their s orbital electrons is being used up in a hybrid bond.
No. The oxygen, I'm not drawing all of oxygen's orbitals in my picture here. Oxygen has an s orbital that has a lone pair in it, and it has another p orbital that has a lone pair in it. But I'm not drawing those because that gets really messy.
Yeah, absolutely. Just for my mind's sake, I mean, is there just the one other s electron that's still hanging around with the oxygen, or?
Well, which s electron? The oxygen's?
Yes.
Oxygen has 2 s electrons,
Right.
and they're together, paired up in the s orbital.
It's just one more.
It would be a circle here,
Gotcha.
okay?
It would be just like the carbon one, 2 going up and 4 going.
Those are actually 2 carbons.
So
If you drew all of them, it would look just like carbon.
let's see. Back here. How far back? I don't know. I know it's trippy, huh? Okay, So here, this is not hybridized, but here they're showing, here's the s orbital, and here's one p orbital, and here's the other p orbital. So I didn't draw the unhybridized p orbital with a lone pair. I didn't draw the s orbital with a lone pair. But they're there. Okay, let's stop.